last time, what did we do? We're doing differentiation of different kinds of things. We learned how to differentiate e to the x. E to the x is e to the x. The derivative of sine, cosine, the derivative of cosine, negative sine. And we combine those with our product rule. What's f times g prime? F prime g plus f g prime f, whatever you prefer, f g prime. We had our reciprocal rule, 1 over f prime negative f prime over f squared, which we used to prove the quotient rule. This is all, let's get these things loaded back into our brains. F over g prime is low d high minus high d low. Yeah, but I can never remember the rest of the song. Square the thing that's below, whatever, okay. Over the square of what's below, okay, great. Good, we'll use this to do derivative of secant as secant tan, derivative of tan as secant squared, like these kinds of things, right? We're happy with this. All right, let's add some more, not rules, but I would say shortcuts to our arsenal. So here's a really weird function. So let's try to work out this function. F of x is equal to, I don't know, sine of cosine of x. Let's just do something crazy. What the hell is this thing? All right, I know what sine looks like. Sine, here's a graph of sine. Sine is this kind of thing, right? Cosine by itself is this kind of thing. So whatever cosine is doing, cosine is 2 pi periodic. So as I put in values of x that are shifted by 2 pi in either direction, I'm going to get the same values. So this function will be 2 pi periodic. But what in the world does it look like? Well, as x ranges here, let me think of this as a function of w. So this is a graph of sine of w. Okay, and this is a graph of cosine of x. So as x ranges, let's say from 0 to 2 pi, so here's 2 pi. Once we know what the graph of this thing is in this range, we know everything about it. So what happens to cosine? Cosine, don't do that. What are you doing? That was weird. Cosine ranges from minus one to 1, right? As x ranges, the value of cosine ranges from -1 to 1. So the value, if I think of this as sine of w, where w is, I'm thinking of w as being cosine x, if w will range from, yeah, -1 to 1, 1 to -1. So I only care about the values of sine from -1 to 1. Now this is pi, and this over here is pi over 2, horribly drawn. Pi is 3 and change. Pi over 2 is 1.5 and change. So 1 is somewhere over here. So this is the value. It's not there's nothing nice about this number. It's just sine of 1. 1 radian, right? 1 radian. That's where the function starts. That's where this function f starts. So it's the combination of this function and this function. So f starts at, if this is 1, somewhere over here is sine of 1. And that's the value of f at 0. It's also the value of f at 2 pi, because it's going to be 2 pi periodic. Okay. And then cosine is going to start dropping when it gets to pi. Cosine is going to be at -1. So that means w is going to start dropping from 1 down to over here, -1. When x is at -1, when x is at pi, w is at -1, and when sine of -1 is whatever it is, it's sine of -1. Okay, so here's sine of -1. Sine of -1 over here at pi is some value, and it's a little bit less than -1. I mean, a little bit less negative than -1. Okay, so we got 3 points so far on the graph. In between, it's going to do something nice and continuous and smooth. So it's just going back and forth like this. So it's doing something. I don't really, I can't really draw it. It looks like a cosine graph, but it's not. It's some weird thing. Okay. And the question is, what is the derivative? Despite the fact that this weird thing, okay, I don't know what it looks like. Let's try to figure out what its derivative is. Is everyone clear on what we're trying to do? Okay, so we have a complicated function. We've taken a composition. This you would write as sine composed with cosine. Okay, so we could say f is sine composed with cosine, which means f of x is sine of cosine of x. Right? Let's work out what its derivative is. Okay. So the question is df dx. How would we do this? Df dx is the limit as what? U goes to x, if you prefer, of the function. The function is sine of cosine of x, sine of cosine of u, sine of cosine of u, minus sine of cosine of x over u minus x. For some strange reason, I've written it in this product of two fractions way. What the heck is going on? I know what happens when sine changes, and I know what happens when cosine changes, but now I'm asked to have what happens when sine of cosine changes. Let me multiply the top and bottom by the thing that I know how to change in terms of sine. Let me multiply by cosine of u minus cosine of x on top and bottom. Cosine of u minus cosine of x. Do you see how I would have come up with that as something to multiply the top and bottom by? This cosine of u is what sine is changing into. And this cosine of x is what is where it was. All I did is I multiplied the top and bottom by the same thing. But these are two things whose limits we can try to evaluate. Okay. So let's see how to do that. Well, the limit of a product is equal to the product of the limits as long as both limits exist. So let's see if the two individual limits exist, and then we can take the product, the limiting product. So what are the two limits that we're thinking about? So let's think about two limits. One limit is this limit. What happens to this limit as u goes to x? The numerator goes to 0, but the denominator also goes to 0. This looks like the definition of the derivative of cosine. Exactly. This looks like cosine prime, cosine of x prime, which we know is negative sine prime, but let's leave it as that for a second. Right? You see how this is, when u is very close to x, this is very close to the derivative of cosine from the definition of cosine, from the definition of the derivative. What is happening here? Well, so let's say that this cosine of x, so we already said that w was the value of cosine of x, and let's give another name, wv. Let v be the value of cosine of u. Okay. Now, as u goes to x, what happens with v and w? As u gets closer and closer to x, is the function cosine continuous? So as u gets closer and closer to x, the value of cosine of u gets closer and closer to the value of cosine of x. So in other words, this variable v gets closer and closer to w. W is not moving. X is fixed, w is fixed. W is just the value in this plane, right? This was the function w equals cosine of x in the w plane. Okay, so as u gets closer and closer to x, v gets closer and closer to w. What if we change variables on this part? Let's write this as the limit of sine of, so I'm changing variables instead of u, I'll write v is cosine of u. So this is sine of v minus sine of cosine of x is w, exactly, divided by, does everybody see? v minus w, v minus w, and this is the limit as v goes to w. We've made this change of variables. When u gets closer and closer to x, that's here. If I have some value x and I have some value u that's getting closer and closer to x, then this is some fixed value w. This is some value v. U is getting closer to x, v is getting closer to w. But then I look over here in the w plane, I have my fixed value of w, whatever that was, and then there's a nearby value v, and the nearby value is getting closer, and now I'm taking this ratio. Okay, so this limit as u goes to x of sine of cosine of u minus sine of cosine of x divided by cosine of u minus cosine of x, just this part itself, we can think of as the limit as v goes to w of sine of v minus sine of w divided by v minus w. Does that make some sense? Will? Yes. Let me try to explain the graph again while also having this there. Okay, let's get a little color. So u is getting closer and closer to x. That's this u and x. That's this limit as u goes to x. Then that gives me a value w, which is the value w is cosine of x, and v right here, v is cosine of u. Okay, so v is the value of cosine at u, w is the value of cosine at x. So that's just the cosine function. Now I'm going to apply the sine function to the cosine function. So this compound function, which means whatever the value of w was that came out of that value of x and u. So here's my value of w, and here's my value of v, and this v is getting closer and closer to w. V is getting closer and closer to w as u gets closer and closer to x. So if we make this little change of variables here from u going to x into v going to w, this is what these values turn into. Okay, again, this is not a proof-based course, so I will not ask you to prove things like this, but I would like you to understand that we're not just pushing around symbols, that you can see what's going on. Andrew.
Can you explain again how and why we multiplied by that?
So we just multiplied top and bottom by 1. So we haven't changed anything. The original definition of the limit is the function at u minus the function at x divided by u minus x. And we had this idea to multiply the top and bottom by something slick. That slick thing is this cosine of u minus cosine of x, because that's what sine is changing by, right? Again, each of these things that we're going over was a PhD thesis in 1710. So this is something that took people decades to figure out, and we're going to do it in 10 minutes because we know what all the right steps are. We aren't stumbling in the dark anymore. So the idea to put the cosine of u minus cosine x up and down is something that could take 10 years. But once you have that idea, then you can see what the consequences of that idea are. Okay, so we're skipping those 10 years. We're going straight to the idea. What is happening in this limit? What is happening? What is this limit? Sine of v minus sine of w divided by v minus w. The limit as v goes to w. Other than Peter? Yeah, exactly. It's the derivative of sine. It's the derivative of sine. It's the derivative of sine, but where? Not at x, at w. It's the derivative of sine at w. Derivative of sine is cosine, okay? So what we've shown is that the derivative of sine of cosine of x as x changes is equal to, so these two limits do exist, so the limit of their product is also the product of the limits. So that's this product here turning into that product there. And the derivative of sine is cosine at w. What's w in terms of x? Cosine of x. So it's cosine of x. It's not cosine squared. It's cosine of x times, what's the derivative of cosine? Negative sine of x. Okay, that's the derivative of this complicated function. Is there anything special about the function sines and cosines. No, we could have done this for any function, and that gives us the dreaded, infamous, whatever, chain rule. The chain rule. This is called the chain rule. When you have a chain of functions, if you have f composed with g, let me write it as f of g of x. This whole thing, if you want to differentiate a chain of functions, one applied to the other, then what did we get? We got the derivative of the first function evaluated at the value of the second function. So it's the derivative of the first function at the value of the second function times, this is where the chain rule comes in, times the derivative of the second function. So each of those functions is making a change, and the net change is the product of the two changes when it's a chain of functions. So we were guessing that the product rule, if you take a function times another function, it would be the product of the derivatives. That's not true. It is true when you chain functions together. So you apply f, then you apply g, the derivative will be the product of the derivatives, but at their appropriate places. You don't take the derivative of f at x, you take the derivative of f at g of x, because that's where f is getting its values. Okay, does that make sense? Let's do 100 examples of the chain rule until we get good at the chain rule. Derivative of d dx of e to the x squared plus 1. Let's do a couple together. Raghav, you want to answer. I know you know the answer. I want people to have time to think about it. Take 2 minutes and try to figure out what's going on. What's the function f? F of x is e to the x, e to the x. What's the function g? X squared plus 1, x squared plus 1. So this is then f of g of x. Okay. Everybody see that? Give me a thumbs up when you have the derivative. Okay. Half of you have seen this before, so it's easy for you. And some of you are seeing this for the first time. And so you're trying to parse out what all these damn symbols mean. Should we do it together? Okay. What's the derivative of f? The derivative of e to the x is itself, e to the x. What's the derivative of g? 2x. So the formula is the chain rule, the shortcut. It's not a rule, right? Rules are imposed. Shortcuts are things that are supposed to help you, so you don't have to do this kind of a calculation every single time. The shortcut is f prime, that's e to the g of x. So it's f prime at g of x. So it's e to the x squared plus 1 times g prime, which is 2x. Okay. So pretty easy. You just differentiate the first function at the value of the second function times the derivative of the second function. You remember last time somebody asked about the derivative of e to the 2x? You remember? And we said, well, you can do it by thinking of e to the 2x as e to the x times e to the x and use the product rule. And the product rule will give me e to the x times e to the x plus another e to the x times e to the x. That gave me 2 e to the 2x. But now we can do it with the chain rule. The chain rule will say it's the derivative of e to the x is e to the x, so it's e to the whatever. And the chain rule, what's the derivative of 2x? 2. So we get the same answer in 2 different ways. We have not broken math. Let's do a complicated one. Somebody shout out a complicated function. Give me some functions. 3x squared plus 2x. 3x squared plus 2x plus 1. And what should we do to this? Cube it. Okay, cube it. Anything else? Take the square root of that. That's like raising it to the 3/2 power. We can do that. How about sine of this whole thing? Sine of this whole thing. What is the derivative? Now, the reason it's called the chain rule is if you have f of g of h, if you chain a whole bunch of functions together, right? You're chaining operations together. Each one will have its own derivative times the derivative of what's inside, but the chain rule tells you the derivative of what's inside. In other words, let me write this down over here. If I have f of g of h of x, and I differentiate that, so let me put the of x in here, the derivative of that, well, this inside function we can think of as one function. So I'll get f prime of g of h at x times the derivative of the inside function. But what's the derivative of g of h? We'll use the chain rule. It's g prime of h times h prime. These are all at x, h of x. Okay, so you can chain, when you apply the functions in a chain, you can differentiate in a chain. All right, what's our first function? Sine. So I'm going to differentiate sine and get cosine of whatever is inside. I leave whatever is inside alone. 3x squared plus 2x plus 1 cubed times. Now I forget about the sine and I have the cube function. What's the derivative of the cube function? 3 times the thing squared. The thing I leave alone. The inside I leave alone. 3x squared plus 2x plus 1 times, now what's happening on the innermost function? Exactly. Now we're getting good at this. 6x plus 2. And that is the total derivative. Any questions on this? Does this make sense? What happened? You don't have to simplify. No, no. By the way, let's do one more version of this. Just a simple version. Or Will, you had a question? Right. So f in this case, in our example here, f is sine. F of x is sine of x. G of x is x cubed, is this thing cubed. That's the cube function. And h of x is this polynomial, 3x squared plus 2x plus 1. So that's f of g of h, which really, it happens in reverse. You take x, you do h to it, meaning you square it and multiply by 3 and add twice x itself and add 1. Then you do g to it, meaning you cube the whole thing. Then you do f to it, meaning you take sine of whatever that answer was. And now when you differentiate f at the value that it's being evaluated at. You multiply that by the derivative of what's inside. The derivative of what's inside is, again, we use the chain rule. We chain the chain rule. 3 comes down and I get 3 whatever squared. The whatever is left alone times now the derivative of whatever. Let's do one more example, Peter. You can just leave it like that. Yeah, just leave it like that. Ying. Sure, you can let it be u. Yeah, and then you write 3u squared, but then times u prime, times the derivative of the u. Yeah. Let's do another derivative of, let's do an easy one. How about the derivative of x plus 1 squared? So by the chain rule, the derivative of the square function is 2 times the thing to the first power, 2 times the thing. And what's the, let's make it slightly more complicated. How about 3x plus 1? So 3x plus 1 quantity squared. So that's 2 times 3x plus 1. And the derivative of 3x plus 1 is 3. Okay, so let's see. I get, well, I get whatever I get, all right? I don't have to simplify this. But we could have done it a different way. If we square this out instead, we'll just get a nice little polynomial. Right? If we square this out, 3x plus 1 squared is 9x squared plus 6x plus 1. The derivative of that is, what am I getting here? 18? 18x plus 6. And look at that. 3 times 3 times 2 is 18x. And 2 times 1 times 3 is 6. So we have not broken math. Nimmer. This 2. The derivative of x squared, is 2 times the thing to the first power. So I just took the function x squared as the outermost function. And then the 2 came down and was raised to the first power. Does that make sense? Should we do one for the quiz? All right, let's do a quiz. Let's do a nice one. What's the, okay, so quiz. What's the derivative with respect to x of, I don't know, cosine of 2x squared plus 1? All right, take 5 minutes. Tell me what the derivative of cosine of 2x squared plus 1 is. Let me scroll up so you can see the chain rule. Well, let me just rewrite the chain rule somewhere so you have it to stare at. The chain rule says that the derivative of f of g at x prime is f prime at g of x times g prime of x. Give me a thumbs up when you got it. Give me a hand if you need a hint. Some of you are very good at this already. Others are seeing for the first time. I want to make sure you have plenty of time to work. Anybody still working? Everybody's done? Okay. Post-it note, you did a post-it note? Whatever's supposed to. Okay, let's do it. Okay, the first function, I mean, the last function, really, the last function we do, you start with x. You're going to square it, multiply it by 2, and add 1. Then you need to take cosine of that. So cosine is the last thing we do, but it's going to be the first thing we differentiate. The derivative of cosine is negative sine. So it's negative sine of what's inside, 2x squared plus 1, times the derivative of what's inside, which is 4x. Okay, if you got this first thing, give yourself a point. If you got the 4x, give yourself another point. And if you multiplied them instead of doing something crazy, give yourself another point. Hand them all down. All right. This is pretty easy, I hope. I hope you're finding this easy. We got one more topic in 10 minutes. I think we can do it. Because it's an easy topic once you know the chain rule. And that topic is implicit differentiation. This is something that people find difficult, and I never understood why, because it's a very easy thing. What just happened? Oh, that was weird. Implicit differentiation. So taking derivatives, implicit as opposed to explicit. When it's explicit, we have like y is a function of f of x, right? But y is implicitly a function of x. This is secretly a function of x. I'm not writing y of x. I'm just writing y. But we know that y is changing as x is changing, right? So y is sort of implicitly or secretly a function of x. So let's do an implicit derivative. Let's look at the graph of x squared plus y squared equals 1. So here's our example. What is this? Unit circle, exactly. Okay, so we have this unit circle, x squared plus y squared equals 1. Implicitly, y is a function of x. In fact, it's not really a function of x because this doesn't pass the vertical line test, but y changes as x changes. And we would like to know what, so this is just an equality. How does either side change? How do both sides change as x changes? So let's differentiate both sides. Differentiate both sides. Differentiate both sides. So if I differentiate both sides, I'm looking at d dx of x squared plus y squared equals d dx of the constant 1. What's d dx of 1? 0. Okay. What is d dx of x squared 2x plus what is d dx of y squared? Y is implicitly a function of x. Beautiful. So the chain rule says y is a function of x, and then we're taking a function of that. So let's just apply the chain rule. The derivative of something squared is 2 times that something to the first power, and the chain rule says times, well, let me not write it to the first power so you don't get confused with prime, times the derivative of y itself, which is just dy dx. And look at what we've learned. This is equal to 0. We can solve for dy dx very easily. Let's solve for dy dx. Solve for dy dx. Sorry? Did somebody say something? No. Okay, I can divide up the 2's. I can subtract. So dy dx, we can just do this in our heads. I move the x to that side. I get a negative x, and I divide by y. So it's negative x over y. Okay, let's think about that. At any point, x comma y, whether it's on the upper half or the lower half of the circle, at any point x comma y, what is this slope? Julius. Well, the slope of just the line from 0 to this point. The change in y is just y over x. Yeah, isn't that, yeah, not a trick. It's kind of a trick question because it's too easy. Y over x. Okay. What is this slope? The slope of the tangent line is perpendicular to it. So what's its slope? It's negative reciprocal, negative x over y. That is exactly what we just saw. Yes, Will. The whole thing is equal to 0 because ddx of the constant 1 is equal to 0. So once you have these two sides being equal, if you differentiate both sides, you get something that involves x's and y's and the derivative of y with respect to x. So if you have this equation. This is the derivative of y with respect to x. Let's solve for it. So I can divide the 2's out. I can divide out the 2's. Bless you. I'll move the x to the other side. That becomes a negative x. And I divide by y, and that becomes negative x over y. And what we learned is that this, on a circle, the tangent line is orthogonal to the direction from the origin to the point. That's exactly what it means to be moving along a circle. Okay? Let's do one more example. We have time for one more example. And you'll get the hang of this. This is something that's very simple if you are comfortable with the chain rule. Okay, let's say we have, so here's another example. We have the following curve. It's a weird curve. X cubed plus y cubed minus 9xy equals 0. I have no idea what this thing looks like. It's going to be some weird whatever. It's a curve, right? If you give me a value of x, I'll get some values of y. And as x changes, the value of y changes. It's not necessarily a function. It's just a graph. It's just some graph. Okay, these are all the points that lie on this. Let's look at the point 2, 4, I claim is on the curve. This point is on the curve. So 2, 4 is a point on the curve. Okay, so this is this point P. Is it actually on the curve? If I take 2 and I cube it, that's 8 plus 4 cubed is 64 minus 9 times 72. 9 times 8 is 72. Okay, equals 0. Good. So that is indeed a point on the curve. So 2, 4 is a point on this curve because it satisfies when x is 2 and y is 4, that satisfies this equation. Let's differentiate. So differentiate both sides. Differentiate both sides. Well, the derivative of 0 is 0. And what's the derivative of this? Implicitly, with y being implicitly a function of x. Hard. That's right. That's right. So I would have to say implicitly y is a function of x. Or if all you're seeing is x's and y's, the what's it called? The standard, what's the right word? The convention. Thank you. The convention, brain freeze. The convention is that y is the function. Y is the function and x is the free variable. Okay. The convention. Thank you. The convention is that y is always the function of x. Okay, so if I differentiate, and that's why I say d dx, x is what's changing. Y is implicitly a function of x cubed plus y cubed minus 9xy. So let's differentiate this. The x cubed becomes 3x squared. The y cubed becomes 3y squared times y prime. dy dx, right? That's the chain rule, minus 9 times the product rule. The product rule is the first thing times the derivative of the second thing, that's y prime, plus the derivative of the first, which is 1, times the second. Jenny. Y prime and dy dx, same thing. Yeah. Okay, I'm just writing slightly fewer letters. Okay, that equals 0. That means I have to solve for y prime. I have two places where there's a y prime. So let's do this a little bit slowly. So let me move the 3x squared and the minus 9y to the other side. So I get plus 9y minus 3x squared is equal to y prime. Y prime is the thing that I'm trying to solve for, times 3y squared minus 9x, 3y squared minus 9x. And so y prime is equal to 9y minus 3x squared divided by 3y squared minus 9x. And the question is, I didn't specify what the question was. The question is, what's the slope of the tangent line at P? So I want to evaluate this at the point 2, 4. So I want to evaluate this at the points 2, 4. That's our point P. So what is that? That's 9 times y is equal to 4, minus 3 times x is 2 squared, all over 3 times y squared, that's 4 squared, minus 9 times 2. That is some number. That number is the slope. Implicit differentiation, very easy once you have the chain rule. The chain rule, very easy once you get used to what the rule is, what the shortcut is.